Neil, our technician, has suddenly got inspiration from his old physics teacher. He's devised a machine which will allow him to put a high current through a piece of thin wire. And as he turns the knob, the current goes up and up and up until the wire fails.
Now I'm ready when you are for this one.
So we started with copper. What happens is that as you put the current through the copper, it gets hotter and hotter and hotter. And in this case, copper melts before it catches fire. So suddenly you see the wire sagging down and down and down, and eventually it breaks. And as it breaks, there is a flash as the copper vaporizes. And you may remember that copper gives a nice green color in the vapor. So you see a very quick flash of green light. So Neil had a great ambition to try and burn aluminium. So he got a piece of aluminium wire and heated it up. But like copper, aluminium melts before it catches fire in air. So suddenly it starts sagging, 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 and after a little bit, it breaks. Neil was a bit disappointed. Nothing burned. So we tried magnesium. Didn't have magnesium wire, so we tried magnesium ribbon. That's relatively flat material. And as you heat that, because the heated metal expands, the magnesium started arching upwards, and then suddenly it drooped. But as probably many of you know, that once you set fire to magnesium, it keeps burning. So the whole lot burnt away with clouds of white sort of smoke, which essentially is finely divided magnesium oxide. Magnesium is a metal that once you light it, it generates so much heat that the burning becomes self-sustaining. It's probably because the metal doesn't conduct away the heat very much from the area that's burning, whereas aluminium and copper, if you set it on fire and remove the source of heat, it quickly goes out. Probably the metal just cools down too fast. Neil suddenly remembered he had some special wire. He took Brady to his special store. He calls it the dark hole. Doesn't want me going there. I might start taking things from it. In the dark hole was the remains of a superconducting magnet, a very powerful magnet that was used in an instrument some years ago. The magnet consists of a coil, and Neil cut off a piece of this alloy. The wire that's used for these magnets has to be insulated, otherwise it would short circuit, and it's insulated with varnish. So as it heats up, there's a bit of smoking as the varnish vaporizes. Slightly disappointingly, it behaves much the same as the other metals. Sags, flashes, and breaks. Next, Neil produced a piece of tungsten wire. Tungsten wire is what's used in old-fashioned light bulbs. It was really interesting. As you heat it up, it gets hotter and hotter. Tungsten has the highest melting point of any of the metals that we used. And it starts to burn, doesn't melt at all, and just gets thinner and thinner and thinner until it fails. He ended up with quite a terrifying looking spike of really narrow tungsten.
So, Professor, this did fail quite quickly, but light bulbs don't fail quickly, ideally. What's the difference between this and a light bulb?
The difference from a light bulb is that in a light bulb, the tungsten is not as hot as at the end of Neil's experiment. And of course, the bulb itself is filled with argon gas rather than with air. Neil and I were both really quite fascinated by this very narrow spike that is made. And I think it is because one part of the wire must have started getting thinner than the rest and therefore hotter, and therefore preferentially the hottest part will have burnt fastest. Brady really wanted to do gold. Neil was a bit reticent. Gold is expensive. So he put a glass dish underneath. Now, I must say that gold was probably the most disappointing of them all, because it heated up, it melted, it broke. It didn't give a really very convincing flash. Gold doesn't have a beautiful green colour like copper, but Brady was satisfied, and Neil didn't lose any gold. I think the most exciting metal, and this was a real surprise, was molybdenum. When we heated up molybdenum, even when I was watching the camera from the distance, there seemed to be some sort of pulsating on the picture. And when we looked at the metal afterwards, it was extraordinary, because instead of having a smooth wire, there were little blobs of molybdenum metal all the way along the wire, and these blobs were really quite evenly spaced. Now, it turns out that this phenomenon has been seen in exploding wires using very high-speed cameras. I think it's unusual. I and none of my colleagues had seen anything like this before. Now, you probably, or some of you who are specialists in this area, probably have some really good explanation of why this happened. I think what happened is that the molybdenum metal began to melt on the surface of the wire. So you imagine the wire covered with a thin layer of liquid. And because liquid has surface tension, this is why liquid forms drops. I think that the liquid separated into little drops because the surface tension pulled it together. And so you get what would normally be little drops of liquid, but they solidified. So we've somehow got them fossilized along this wire. All my colleagues that I've shown these bits of wire to have got really excited. It's really surprising that you can get such an even spacing. I did a bit of research on this phenomenon, and I came across a word I'd never heard before called unduloids. Unduloid is the word that mathematicians use to describe this sort of object. I would be very interested to hear from any of you who has a really good explanation of what happened. Neil thinks that the spacing might be related to the frequency of the mains. So he's keen to try and use direct current rather than alternating current and see whether we get the same effect. I think there'll be no difference. I had the idea that we should turn the apparatus through 90 degrees so the wire is vertical, and it would be much more difficult for it to sag. And what we found was indeed it didn't sag so much, at least until it broke, and we got a much better shot of the flash of green light as the copper vaporized. There was still slight bending, but it was much less than before. Just as we were packing up, I persuaded Neil to make a coil of copper. We put this coil vertically. My idea was that the coil would be floppier than the straight piece of wire, so it might sink more. But then it collapsed quite spectacularly once it had broken. But I think chemically what was interesting to me was that if you looked at the bit that was broken, you could see the black copper 2 oxide on the surface of the copper, showing that there was at least some reaction with oxygen, but very much less than, say, the burning magnesium. I was really grateful to Neil because he devised a demonstration, which almost turned into an experiment, which made me think. I never thought that a piece of molybdenum wire could be in the least bit interesting. And here I am, the day after Neil did the experiment, still thinking about it. And anything that makes scientists think is really good. And anything that makes us think differently is brilliant.